Hello, good morning everyone. I'm Dr. Paula Gomez with the Machine Learning and Data Analytics branch at the Georgia Tech Research Institute. Today are here with me my colleagues Dr. Khatereh Hadi, Dr. Swarts, Dr. Olga Kemenova from GTRI, and in collaboration with Dr. Marcelo Bernal from Perkins and Will Design Process Lab. In this study, we explore the role of architecture within the COVID-19 pandemic. Our research focuses on the role of building and smaller scale spaces on the virus spread instead of the large scale environments. In the context of the pandemic, most of the modeling efforts focus on understanding the virus spread patterns in large scales, such as urban scales, but not in enclosed built environments. Various predictive models have been used to study virus spread dynamics: mathematical, statistical, agent-based simulation modeling methods, regional, urban, country-specific, and worldwide scales. We propose a comprehensive parametric modeling approach of the most significant parameters shown to have an impact on the COVID-19 spread in educational settings. This publication presents the model by aspect, extending our initial research. The proof of concept is a K-12 educational setting provided by Perkins and Will. Our spatiotemporal model integrates 4 types of data into a single model for analytics: spatial parameters, organizational protocols, occupants' behavior, and virus characteristics and preventative policies. We made several models to finally integrate them into a simulation model that calculates 2 outputs: probabilities of spatial contamination and probabilities of contagion risk. The first one is assigned to a spatial cell, 1 cubic feet, and the second one is assigned to an agent at a specific time. The modeling parameters include building parameters such as layout and materials of surfaces, agent parameters including the health status of the agent, distance to the source, and time of exposure, and virus characteristic parameters including survival time of the virus in different materials and number of known COVID-19 cases by population. To implement the spatiotemporal model, we integrated expert knowledge from several sources. These are examples for calculating the risk of airborne COVID-19 by population, PPE level, frequency of space visits, and occupancy rates, and the risk of coronavirus transmission in different settings and protective equipment. Also, for agent modeling, we included the parameter distribution of health status connected to contagious period. In this chart, you can see the distribution of asymptomatic agents compared to critical symptomatic agents. You can see the majority of the agents will be in the mild-moderate symptoms, 55%. However, for educational settings, the distribution does not replicate the total population distribution, since the majority of the agents are children. For fomite transmission, which means surface-to-human transmission, we included parameters such as the survival time of the virus in different materials. As shown in the graph below, the virus stability on aerosols, first figure to the left, is more than 3 hours. And in copper, the next figure, the virus stability is less than 20 minutes. These parameters are superimposed to the daylight that each surface receives during the day, since the virus stability is reduced by daylight exposure. To model the students' movements and activities, we use the possible path in a layout. To simulate spatial occupancy patterns based on student schedules and processes, we defined agents' profiles with parameters such as arrival time, activities and flows, time spent at each location, and the health status and PPE level to calculate the exposure risk. For agent modeling, we compared scenarios based on the redesigned occupancy rates proposed by the K-12 capacity guidelines by Perkins and Will Human Experience Lab. Then simulated these scenarios in any logic to calculate the numbers of interactions between agents and time spent in certain locations. Afterwards, we included computed fluid dynamics simulations to assess how the airflow dynamics in enclosed spaces impact the spread of the virus. The images show the very first study on virus spread due to an HVAC system in a Chinese restaurant, to the right. The image to the left shows a visual assessment of a CFD simulation that traces airflows of a K-12 classroom. Contaminated airflow is shown in red, while clean airflow in blue. The inlets and outlets are located on opposite walls in image A, and on the ceiling in images B and C. Then, a sick student that is coughing with no mask is sitting next to the inlet in image A, below the inlet in image B, and below the outlet in image C. You can visually assess the better scenario with less contaminated air floating inside the classroom. This diagram shows the integration framework for the spatiotemporal model. From left to right, you can see how the inputs feed into CFD and pedestrian simulations. These simulations produce intermediate outputs, which are combined with additional inputs into a stage of calculations. The calculations include aerosol, droplet, and foam edge spread. The outputs are split between zonal exposure and occupant exposure accumulations. As presented, the spatiotemporal model integrates spatial and temporal parameters into a comprehensive model to generate two metrics as statistical probabilities. The metrics are the probability of spatial viral contamination as an attribute of a cell, and the probability of agent exposure assigned to an agent at a specific time and location. These probabilities are directly related to the sequence of activities and exposure to the contaminated spaces over time. We have modeled aspects of a K-12 environment to understand the role of architecture in this pandemic, in conjunction with human behavior. We have integrated epidemiology and virology expert knowledge into the models. We have calculated the potential impact of a layout configuration on the spread of the virus, depending not only on the program, but on the programming of spaces. Future work includes fine-tuning of activity categories for the spread amount, more virus characteristics such as minimum infectious dose, indoor positioning systems for integrating real human behavior, and contact tracing methods to validate the model. Thank you very much, and please feel free to reach out to us for questions. See you!